Okay. Hi everyone. It's Happy New Year to everyone. We're recovering after a long break, Christmas break, and it feels like Christmas is still with us here because I have the great pleasure to welcome and introduce our today's guest and speaker, Professor Ingo Runkel of Universität Hamburg. So Ingo is a renowned expert on low-dimensional field theory, in particular conformal field theory. In particular, he's developed together with Christoph Schweigert and Jürgen Fuchs and Jörg Fröhlich a program of functorial quantization of two-dimensional conformal field theories, in particular rational conformal field theories. He's also one of the pioneers of the application, description, modeling of defects in field theories. And this is what makes my introduction somewhat more personal, because this is what brought us together almost 20 years ago when I was a postdoc with Ingo at King's College London, and where we've worked out a fully fledged description of two-dimensional field theories with the Vesumino term and managed to extract rather non-trivial non-perturbative data of rational conformal field theory from the underlying Judd theory. So with that said, I'm over happy to give the floor over to Ingo, who's going to introduce us to topological symmetries and their gaugings in two-dimensional CFT and the corresponding three-dimensional topological field theory. Here, Ingo, the floor is yours.
Thank you very much. Thank you for the kind invitation and introduction. Does the sound work okay enough?
Yeah.
Very good. Then, okay. So I'm as we discovered in our pre-chat, there was some confusion about the time. Let's see if I got the format correct now. So I have sort of two bits, which hopefully will take about 45 minutes, and there'll be a break in the middle. Did I get that right? And so the first bit is maybe the less organized bit, which gives you the opportunity to ask more questions. So my plan was to, because this talk will not have so much geometry, if I'm very honest, and it'll maybe have more algebra. So rather than starting with something very abstract, I wanted to start with something very concrete. And so I want to just talk about the two-dimensional Ising model. So that'll be part one. That'll be the first 45 minutes, and I'll try to explain how, from various perspectives, one can understand and describe topological line defects in this two-dimensional Ising model. And then so the first part is sort of a mix of a slide talk and me writing on the slides. And then part two is more of a slide talk, and I will take maybe a more broad, more abstract perspective and try to say similar things, but now on general models. And I'll try to go a bit further than I get in part one. So that's the plan. Goodie. And so please interrupt me if you've got questions. I'm happy to try and answer them. So I will start with reminding you about the two-dimensional statistical lattice model, which is the Ising model. And all the material I present in part one is well known. I didn't give detailed references. There's this a survey article which contains what I will be saying and contains references if you want to see more details. Good. So what's the Ising model? So in two dimensions, you think of having a square lattice, like in my picture here, and the square lattice has sides. And to each side, you assign a spin variable, plus or minus 1. And then you want to do statistical physics. So you first say, well, if each side has such a spin, I will collect these in a function. Let's say S is a function which goes from the sets of all sides to just plus or minus 1. And that function says what is the spin at each side. And then for each such a spin configuration, so that's maybe a spin configuration, you can assign an energy. So what would that energy want to be? So what we will want to model here is a ferromagnet. So we want the energy to be low if the spins are aligned. So if they're both plus or both minus, and we want the energy to be high if they are not. And a simple function which does that for you is the following. You take minus the sum over nearest neighbors. So that's my notation for nearest neighbors, like this side here. That doesn't work so well. This side here and that side here are nearest neighbors. So whenever they're linked by a bond, and then you write simply Si times Sj, right? And now if both are +1, then the output is -1, so you get a low energy, and if one is plus, one is minus, you get altogether +1, you get a high energy. Right, and so that's the energy per configuration, and we are doing statistical physics, so now we want to look at the partition function, so the average overall states weighted by Boltzmann weight. So partition function, what does that look like? We have Z, and so it's a sum overall such as such spin configurations, and then you get the usual Boltzmann weight, which is e to the minus beta energy of the configuration, where beta is 1 over the temperature, and I'm not the Boltzmann constant 1. Okay. So that would be the partition function. So physically, maybe you would want to be interested to compute correlation functions. How would that look in this model? Suppose you want to correlate the value of the spin at some site I and some site j. That would be defined as the normalized partition function. You normalized by that expression, and then again you take the sum over configurations, and now you take this product as I times Sj, and you weight again with this Boltzmann factor. Right, so that I am hoping many people have seen at some point. Yet this model looks very basic, but it is very interesting. And one interesting feature it has is that it has a high-low temperature or an order-disorder duality, which is called Kramers-Wanier duality. So I want to explain a little bit what that is. So let's see. So firstly, it is an identity on partition functions. Remember, I had this expression up here. And it says if I look at the partition function at inverse temperature beta, then it's equal, well, not quite equal, I'll say, why not quite equal in a bit, to some constant, which depends on beta, but it's sort of multiplied, so to raise to the power of site, so that's a constant which happens at each site, times the partition function now evaluated at a dual inverse temperature, beta tilde. And beta tilde can be given explicitly, that's -1/2 log of the tangens hyperbolicus of beta. Right, and so that looks complicated, but basically what this function looks like is how does beta tilde depend on beta? Well, it looks a little bit like that. Right, and so if I draw the diagonal here, then there's also a point where the model is self-dual, so where beta and beta tilde agree, that's called beta star. And you can also write down explicitly what beta star is. So the nice thing about the Ising model is that you can do many things very, very explicitly. And so it's some formula, never mind. So you can just solve this. It's not difficult. Okay, and I should say what I mean by the hat. So this is up to boundary terms. There's some calculation which works nice in the interior of the lattice, but you have to be careful what happens at the boundary. I'll come back to this a little bit. And I can see Rafael, but I can't see the other people. Who has seen that already? Not so many people. Rafael has seen it. Okay, at least one person has seen that already. Very good. So I want to maybe say one word how you get this. So how would you do this computation? And again, it's sort of instructive if you have never done this before. It's like a statement about finite sums, so there's no magic about continuum limit or field series. It's really very explicit. So how you get there very briefly is you look at this energy and recall what the energy looked like. So that was the expression up here, and you take the sum up here and you write it as a product. So you get the product over nearest neighbors of e to the beta si sj. Right, so this minus sign and that minus sign up here, they cancel. And then this you can rewrite once more. So product nearest neighbors. And then you have a sum. Okay, goes from 0 to 1, two terms of ck of beta times si sj to the power k. And so what's the ck? So that is C0 of beta is, I think it's cosine, it's cosh beta, and C1 of beta is sinh beta. So there's some stupid identity of these trigonometric functions because we only have this very small, right? So this SISJ can just take plus or minus 1 values, so you can just verify this. So what we are doing is we're introducing a new variable k, and so we've rewritten our interaction in this way. And now what we will do to get this relation here is to exchange the roles of k and the spins. And so we keep these k's as the fundamental variables, and we carry out the product or then the sum over the spins si. And if you do this, after a while, you get, I claim, to this relation with precisely this dual beta. It's just a little bit tedious, but it's not difficult. Good. So we have this relation on partition functions. However, if you want to do the same thing for correlation functions, something interesting happens. Namely, if you look at the spin-spin correlator at temperature beta, it doesn't get transformed into another spin-spin correlator, but it gets transformed into a correlator of two disorder fields. So let me write it like this. So this becomes equal to, say, mu I, mu j at the dual temperature beta tilde. And I've drawn this little figure here to explain what this disorder correlator is. So I've again marked my two sites, I and j. So this is where I was evaluating the spins above. But under the order disordered duality, that gets replaced by mark these two plaquettes, draw a line between them like this, and then at all bonds which are crossed by the line, you invert the coupling. Right? So this means that this expression is defined as follows. So that is equal to, well, this prefactor, which we already had up here, which I'll not repeat, then the sum over spin configurations. And now what and the product over nearest neighbors, and now I change my, the energy functional. So I have the dual temperature, and then I get alpha ij times si sj. And this alpha ij, this can be +1 or -1, depending if the corresponding bond between the sides I and j gets crossed by my red line or not. Right? Does that make sense? So I've introduced this disorder in my system. I've introduced a defect. I no longer have a homogeneous lattice system, but now there's this line, and across this line, my energy functional has changed.
But it depends on the line, right?
And it depends on the line, but it doesn't depend on the line, right? Because the dependence on the line isn't there on the left-hand side. Right? So that's an identity. So it would be bad if the right-hand side depends on the line, because the left-hand side does not. But so how do you see that explicitly? So suppose, let me try and draw. So suppose you didn't want your line to go here, but you wanted to maybe go like this instead. Right? I claim that this will give you exactly the same expectation value. And that is so because between each configuration where the line was here and each configuration where the line passes here, there's a one-to-one map between the states, and all it does is it takes, if this was in configuration plus, if you pass the line here, you change it to minus, and then the configuration has the same energy, the same weight as before. Right? So that's important. Does that make sense?
Yeah. Thank you.
And so what this means is that that line is our first example of a topological line defect. Right? I can modify its position. I can make it walk wherever on the lattice, and it doesn't change the expectation value. It doesn't affect the energy of a configuration. And so that's different. So I can't take the line across. If I were to measure the value of that spin, right, then I could detect if I take the line across it or not, because it changes this plus to a minus. So if I were measuring this spin, then taking the line across that side would incur an overall -1. But if I change it across sites where I don't measure the spin by having a correlator where, like, so if I would have, so I don't want to maybe to spend too much time on this, but if this were K, and I would also insert here like an SK, right? Then I couldn't take it across this site because this SK would get a minus sign, so it would not be invariant. Yeah. So that's our first topological defect. And we will later see that this, so I should write this down. This is a topological line defect in the Ising model. And this topological line we will later in a bit understand is related to the Z2 spin flip symmetry of the model. So this will in a moment give us a Z2 symmetry. Right, and so again, so this is an exact symmetry in the lattice model, which works on a finite lattice before doing any continuum limit, setting anything to critical temperature. It's just something which works exactly in the lattice model. Okay. I want to go back a little bit and talk about this. We have to be careful with boundary conditions. So I've drawn some pictures for this. So here's an example in which sense you do have to be careful with boundary conditions. So if you have a non-trivial geometry, like say this 2 torus, so this identified with this and that identified with that, and so I have a finite lattice, but it's periodic.
Sorry, Ingo, just to interrupt you. Whenever you say this or that, we don't see, or at least I
You don't see the
well,
pointer. Do you see a little
No,
hand
no.
which moves around? You do not? Oh.
You can see your hand, I wouldn't call it little, but I don't see the
Okay.
pointer.
Okay. Is that I can't. This is not sure how to fix this. I was hoping I can mark things. So does that show? Wait.
But there's this laser pointer typically in.
Yeah, but not in my Linuxy small. Let me try one thing. I thought there was a way to activate to make this look like a pen. But I forgot how that works. Okay, I'll try to just mark things when I draw. So now I'm saying that this side here is identified with this one here, and this one is identified with this one, and so I'm describing a torus. That was visible, right?
Yep.
Okay.
Good.
And so now I evaluate the partition function at inverse temperature beta for this 2 torus with some finite lattice with periodic boundary conditions, and I ask what's the dual expression if I carry out the duality. And it turns out the dual expression is not just this one here, which one might expect, but instead you get a sum of 4 terms, and you get a sum of just the partition function at the dual inverse temperature, plus 3 frustrated partition functions where you have inserted this Z2 defect, where across this line the interaction parameter has been changed. Right, so one has to take these boundary terms into account, and I will now want to describe this identity, how you get this identity using, again, topological defects. So if you look at old computations of how you would get Kramers one duality. You would indeed just transform the sum, and you would say, well, therefore you've got this identity. And I now want to repeat this computation, but using the language of topological defects. Good. So we have to be careful with boundary terms. That's an example of what can happen. I want to recall you of what topological defects we have met so far. You may think we've only met one, but we have met two because we are mathematicians. So the identity defect, which does nothing, is also a defect. So we've got the identity defect, which just doesn't modify the model at all. And we've got S, the spin flip defect, which changes the sign of the interaction. Okay, is that a question, a hello,
Yes,
or?
hi, nice to see you. Sorry, I'm trying to raise a hand and I have a problem, but
No, it's...
can I just ask, how do you distinguish the cycle of a torus? Because can you remind that you have in these two middle sections, I mean, two middle pictures, how do you know which cycle is which?
It turns out to not matter. If you give me two other cycles, I could use those, and the answer would be the same.
I mean, can you take? Do you consider different number of lattice space along each of the cycle? Would that matter, or?
So I'm not sure if I so I've picked a basis of cycles, right? So I've said I use this, and right, but I could.
This I understand. You could choose another two, but how do you? Could you replace two middle pictures by the same one? The z b tilde for the horizontal line, is it different than for the vertical line?
Yes. So these will be different. So, right. So if I have, say, m times n lattice sites, and
that was my question. So the difference is in the number of lattice spaces.
Right. Oh, I see. That was your question. Yes, yes. So these, of course, if m is equal to n here, then these two expressions would be the same.
Sure. Yeah. Thanks.
And I can't actually see when you do this raised hand. I might, because you're like a tiny corner in my screen. So better just shout at me if you have a question. That's
okay.
Are there more questions or comments?
Yeah, just for me to be sure. So this red line is you just whenever there's a crossing of an edge going across it, then you add this alpha ij.
So the alpha ij I'm thinking of as always being there, but it's not. It can either be 1 or -1, right?
Okay, so maybe I missed it. So what do you do when you add this defect?
So here I've got my defect, right? And so let me write down. So the contribution of each configuration is the weight is given by what I just underlined here. And so it's a product over bonds, right? And for each bond you get a factor. And so what would be the factor for the alpha is 1? You would just get e to the minus beta tilde plus, sorry. And if my alpha is -1, the weight is e to the minus beta tilde. Okay, so I don't know, S. So if this is A.
So the alphas, I forgot that the alphas were attached to the edges, yeah?
And the alphas are attached to the edges. And
those edges which cross the line, they are -1, all others are plus.
So the ones which are crossed by the line are -1, and all the others are plus. All the gray ones are plus, and all the orange ones here are minus.
I see. Thank you.
Welcome.
Ingo, let me ask. So, if I understand correctly, the choice of these cycles should be such that their homology classes form a basis of the integral homology of the torus, right?
Yes.
You need that would be a mathematical condition. So this is basically a sum of spin structures, if I want to think more abstractly.
Yes.
Is that correct? Okay, thank you.
Yes. It's a sum over, well, in the sense that there are also 4 spin structures. That is certainly true.
Yeah, but in a way, that's what you are doing, right? You are flipping the sign of the spin. That's the same as changing the sign of the coupling structure every time you cross it. And
Yes.
because the choice of basis of the homology lattice doesn't matter because these are topological defects, that is exactly a sum of the spin structure. It's equivalent to a sum of the structure.
So
I think.
I'm struggling a little bit to make that sort of precise in the lattice picture. If we talk about the continuum Ising CFT later, then so there is no spin
Yeah, but
structure, right?
in some sense, because the defects are topological, even on the lattice.
Right.
It doesn't really matter whether you are in a discrete case or in the continuum limit, simply because you.
So I agree that it's sort of combinatorially it's the same thing, but I still want to stress that there is no spin structure anywhere here. These are all
Yeah, everything
disoriented.
is discrete, but in a way there is, right? Because these are topological defects. So I don't care that you chose. I mean, if you take the homology class, you can deform them in any way you want. They don't need to sit on the lattice anymore, right? So
Right.
it just becomes a spin structure. Anyway. Thank
But
you.
indeed, so we will. You can say the same thing again later when I talk about the Ising CFT. Yeah, indeed. So it's related to a sum over spin structures. Yeah, goody. So we have got these. So where what was I said we have two defects, and I think I asked if there are more questions or comments, and are there any more? Okay. So we've got these two line defects which we've already met, and this spin flip one here, where I say here and nobody knows what I'm meaning. So this the spin flip one is the one where you change for each bond that's crossed, you get this minus sign. Has the following property. So now I've become too lazy to draw the detailed lattice. So the green bit here, you can replace it by a lattice as fine or broad as you want. And I'm saying that you've got the following exact identity. So this exact identity on the lattice. If you have two parallel lines marked by S, you can connect them as in the second picture, and then you get this identity defect, which I might as well omit, right? So I'm drawing it here because of an equation I want to write in a minute. But really, from the point of the lattice, I could just omit this. So there's this identity which you have. And why do you have this identity? So that's an exact identity on the lattice. And maybe I can quickly draw this up here. So if I had another S up here, then again I could just change the signs of these two spins at these two sides here, and reconnect my picture in the following manner. So this was here, and now I just say, okay, how do I want to do this? I want to delete these two and reconnect them like this, and I can do this at the price of changing the spin in the middle here. Right, and so I've reconnected the red lines, and that's again an exact identity on the lattice. So that's what I'm doing in this picture. And now I want to understand this as a fusion rule for line defects. I have SS is the identity plus nothing, right? And so this is why we can interpret it as a Z2 symmetry. If I apply this, if I have two of these lines parallel to each other, I can just combine them to nothing. So that's my first fusion.
Why is it nothing? You have the lines just in a different direction.
So it's a nothing in the middle. So I'm sort of saying, let me fuse these two lines. So whenever I talk about configurations, I want to do a local manipulation on the lattice. So I want to keep the boundary I want to keep fixed. I don't want to modify anything, and I do some manipulation in the middle. And so in this area where I've drawn the circle, I'm fusing my two red lines, and they go away to the identity defect, which is nothing. So if these were suppose these would continue my lines, they would maybe be a big circle on the lattice like this, right? Then I could indeed move them together and they would disappear totally. So was that the question or comment?
I didn't understand the last part.
So let's see. So I'm saying that, so here I'm showing a local manipulation on the lattice. So here I have these two parallel lines, and on some part of the lines, I'm moving them close together, and I'm saying that the configuration on the left and the configuration on the right have equal expectation values on the lattice, because configuration by configuration, I can map configuration of the same energy one to the other.
Yeah,
Now,
but you have these other lines, these round ones, and you say you push them out of your region, and
so
then
I'm saying,
then they look again like these two parallel lines plus probably one small horizontal one, I guess, right? Like
right.
a
So
U
this
and
this
inverse
fusion
U.
identity you should understand as an identity which holds locally in the sense that I've presented here. And what you could use this for is, suppose you've got two red circles like this, then you can say, okay, this is equal locally to this, but now it's a topological defect, so I can drag this around until I arrive just at a single little loop like this. And then this I can omit entirely. And so therefore, I have two parallel lines, which are also closed, I can remove entirely.
I now understand better. So you're saying that these are topological ones, so you can deform
Right.
your okay, I see.
And
Interesting.
again, on the lattice, it's exact. So it's just an identities of finite sums, and you can sit down and do them. Yeah. More questions or comments? How am I doing on time? So quite okay. Yeah. Now we do a more complicated one, the duality interface. So we have seen in Kramers-Wanye duality that we relate the Ising model at a temperature beta and an inverse temperature beta tilde. So these are different values, right? Unless we had the self-dual points. So we don't have a sort of an endo defect, something which like the spin flip sits in a given model, but we have an interface between two different theories, like the Ising model at different inverse temperatures. And I claim, and I will not explain, that you can write a topological interface. This is the blue line I've written here, between the Ising model at temperature beta tilde and the Ising model at temperature beta. So there's this funny gray part I've drawn, and that means that this interface is a little bit more complicated. It doesn't just live on the blue line. You need to modify it sort of a little bit, the model a little bit near to that line as well, but that's sort of technicalities which I do not want to go into. The important point is that duality interface is again topological, exactly on the lattice. So you can take this interface and you can make it walk another way like this, you can make it walk another way. And by doing this, the interface will transform the original lattice into the dual lattice, and it'll change the interaction for temperature beta to the interaction for temperature beta tilde. So that's quite fascinating if you see that for the first time, that actually this Kramers-Wanye duality between a high and a low temperature Ising model, you can connect these by a tensionless defect exactly on the lattice. That's quite pretty, I find. But you have to change the lattice to the dual lattice. So you don't stay on the same lattice. So it's never going to be, even at the self-dual point, it's not sort of like the spin flip defect, which doesn't change the lattice. It would still change lattice to the dual lattice. Okay, so this, and now I have to let some things drop out of the sky because the computations are finite sums, but they are still tedious. Is that firstly, you can define it. Secondly, it's again exactly topological. And thirdly, it has now the following more complicated property. So again, I'm too lazy to draw the precise lattice. So I'm just drawing green and purple blotches for some fineness of lattice. And green again is for temperature beta. So like here. Why can't I circle things? So that's for temperature beta, and purple is for the dual temperature. And then I have this topological defect, or the topological interface, which can separate these two models. And I can now repeat the computation I did for the spin flip defect. But now the answer is more complicated. So I can fuse these together again exactly on the lattice, but I get a sum of two terms. I get the identity, but I get a second contribution from S. So it's not the symmetry in that sense, in the sense of a group symmetry anymore, but it's still a topological defect. So it's still a symmetry between these two series, easing at beta and easing at beta tilde. So if I want to write this as the fusion rule, it would look as follows. So I would write fusion. I would have D. Maybe I want to write D dual because it's sort of the side on which the beta tilde theory lives changes is equal to the identity plus spin flip. Right? And so that interface D is not invertible. So now we have met a topological interface which has an additional feature which you meet when you study these topological symmetries of models, which is that unlike group symmetries, they do not need to be invertible. So I have the second summoned here, not just the identity. And okay, so it's not invertible, but it still tells us something about the model. Right. So that's our second topological interface. Other questions or comments about this one? Okay. I will now.
Is this related to what people call non-invertible symmetries?
Right. And so that's an instance of a non-invertible symmetry on the lattice. We have to be a little bit careful how broadly. So, I mean, it's not a totally well-defined term, right? So, we have to be a little bit careful with the terminology because it's an interface between two different models. So it's a symmetry which relates easing beta and easing beta tilde, and it's not invertible. So in that sense, it's an instance of a non-invertible topological symmetry, indeed.
I have another question. So what about D dual times D? So is this associative?
Yeah, so if you do D dual, you get the same answer. So it's a, yeah, so if you do D dual D, it's also.
Okay. Thank you.
It's also this. But I'm not going to give any details. Goodie. So let's now do the torus computation again. Torus example. So I have a torus which I filled with some lattice on which I evaluate the easing model at temperature beta. Then, because my defects are topological, I can, like I did here, I can insert a little circle, a little bubble inside which I've got the easing model at the dual temperature beta tilde. Right, and that circle is topological, so I can make it very small and make it disappear. And I claim that it doesn't disappear entirely free of cost, but it gives a constant which depends on some choices of convention. So that's my invertible number lambda here, which compensates the cost of inserting this circle. Okay, but I insist that's an exact identity on the lattice. Okay,
for the correlation functions, right? Not for z's alone would be empty statement, right? Because it's just a number. But you say for the correlation functions also.
It's not totally empty because beta now so the way I set this up, this beta would not depend, this lambda would not depend on beta.
It does not depend on beta. Okay.
It's a little bit, so I did something which I'm hiding from you. So recall that when we did this originally, some way up here, we did have this prefactor. We get a constant for each side. And I've absorbed this constant into redefining what I mean by the easing model. I've added this here. So I sort of added a per side energy to my easing model. And the shift in per side energy does depend on beta. But this coefficient here does not.
Okay.
Okay, but it would also work for correlation functions, but my calculation would look different. So I'm hesitating a bit to say the same works for correlation functions. The answer is yes. but it would look, my computation would look different.
So can I ask, it depends on the number of lattice sites?
Lambda, no.
Or
No, it depends on some, it depends on it, so I have to fix an overall, so like, depends on what you decide your ground state energy per site. So there's the energy per site, you have a free constant where you put it, and lambda depends on that free constant. But it doesn't depend on the size of the lattice, and it doesn't depend on beta. You can choose your conventions for it to be 1 if you want, then it's gone. Sorry, was that the question?
yeah, thanks.
Okay. Right. And because it's topological, this blue line, right, I can now expand it and make it bigger. I can make the bubble very big. That's what happened in my next picture here. So you can still see the bubble, right? So it's like this, and then it is like this, and this. That's my bubble. And so I've just used the fact that I've got a topological interface, and now I use this fusion relation from the previous page to fuse these two lines together and those two lines together, and I get this 1 plus S. So that was the exact identity on the lattice I had up here. So I'm using this twice. Right, and then I get this expression. And now what I didn't show is I can also collapse this bubble away. That'll have the effect of actually eating this constant and giving a factor of 1/2, but I don't want to go into that. And so this is now my sum of 4 terms. Right? So remember what I said earlier, if you do Kramers-Vannier duality on the torus, you get the sum of 4 terms. If you do the computation with defect, that's how you get that sum. So it sort of computes it for you. The fusion rules of this duality defect make you correctly compute what is the dual configuration on the torus. So that's again quite pretty, I find. Okay. So that's what I wanted to say about the lattice model. Quickly running out of time. I still had a bit about the CFT. So we have to see, maybe I have to be, and in principle, I should finish the first part in 5 minutes. Is that correct?
No, it's up to you. I mean, there's a certain flexibility. So you choose the breaking point. Okay, I'll do something. But I want to go. No, let me do the following. I will. I will, rather than writing out everything I wanted to say about CFT, I will use my pre-written notes and hope my handwriting is readable enough. Because now I want to say what I said in the lattice model, I want to say in the continuum model. So I want to go to the critical point, and I want to talk about conformal field theory. So I have to briefly unshare my notes, and I'll share a different set of notes. Give me a second. I'm not quite sure how to do this actually. Not so. So let me briefly stop the share. I'll be back in a second. Okay. And then I have to start the share again. Sorry, how do I start the share again? Okay, is that visible? Yes?
Yes.
Okay.
Yes.
Good. So I want to spend maybe 10 minutes to talk about conformal field theory. So if I do the Ising lattice model and I place it at the critical point, then its continuum theory is a conformal field theory. And we have just discovered that at the lattice model, we had the trivial defect, the spin flip defect, which is within a model at a given temperature, and the duality defect, which relates the model and the model at the dual temperature. Now, if we are at the critical point, temperature and dual temperature are the same. So in the conformal field theory at the critical point, we expect that it has at least 3 topological defects. The identity is something which has a Z2 fusion rule and a defect D, which squares to 1 plus S, because now D is an endo defect of the model, because it's at the critical temperature.
Does the effect that you change the lattice to the dual lattice disappear in the Ising model?
And so the D is a defect which changes the lattice to the dual lattice, but as you go to the continuum limit, right, that turns out that the sort of the shift becomes smaller and smaller and then goes away. So then it becomes an endo defect of the continuum theory. So if the dual lattice of the square lattice again is square lattice, right? But it's just shifted by half a lattice spacing. And so in the continuum limit, that difference disappears, and this duality defect becomes a endo defect of the two-dimensional continuum theory. And it's this D with these underlined fusion rules. Does that make sense?
Yeah.
Okay, so I want to do a little crash course on the 2D Ising CFT. So if you do conformal field theory, you wouldn't necessarily approach it via an action functional, but you do algebra and representation theory. So you'd look at the central charge a half Virasoro algebra. You study its unitary representations, and you find there are 3 of them. And I've called them M1, M sigma, and M epsilon. And they have a state of lowest conformal weight, lowest L0 weight each. And for M1, that weight is 0. And the other weights are 1/16 for the sigma and 1/2 for epsilon. So sigma will later be the spin field, and epsilon will be the energy field, which generates the perturbation which pushes you off the critical point. Okay, the field content, because you have in conformal fields, you have 2 copies of the Virasoro algebra acting, so the space of states decomposes into such a tensor product of left and right holomorphic and anti-holomorphic representations, and I'm claiming this particular sum is the field content of the Ising model. In each of these summands, I can take the primary field, and I find in this way the identity field, the spin field, and the energy field, and they have left-right conformal weights, as I've written here. And then I can use conformal field theory to compute correlators by for 2-point functions. They are fixed by conformal symmetry, and I, for example, find that the spin correlator, I can just compute it out of this 1/16 weight, and I find this. And then you can do more complicated ones. If you actually want to do complicated correlators, you should note that that's actually a GSO projected free fermion relating to Kalin's comment earlier. And but I will only look at this 2-point correlator anyway. Right, and so you get interesting critical exponents, and historically that's how the first sort of exact computation of these exponents came out of this representation theory. Okay. So that's the CFT, but the Ising model also gives you a topological field theory. So there's a 3-dimensional topological field theory you can get out of the Ising model. Again, you look at this Virasoro algebra, or technically you have a vertex operator algebra, but I will not say much about this. And its representation theory is some category. I collect all the representations together, and I call this category IS for Ising. And well, it has 3 simple, 3 irreducible representations, but it's also a tensor category. You can tensor them together. But this tensor product is one of the more complicated things in the theory. It's not just the tensor product over complex numbers, as one may be used to. So there's some intricate construction, which I will not describe. But if you compute the tensor product of this M sigma representation with itself, it decomposes into a sum of 2 things. So there's something which starts to look like the structure we saw in our discussion of line defects in the Ising lattice model. Anyway, so you've got this category. It's a tensor category. It is also braided. You can exchange two representations. It's semi-simple. And the technical term for it is a modular fusion category. And the modular refers to this braiding being non-degenerate. So was there a comment? Okay, so whenever somebody hands me such a gadget, such a modular fusion category, I can get a three-dimensional topological field theory out of it. And so I want to say a little bit what that is, because I'll need that later. So it's a functor. It starts in a geometric, well, rather topological category of 2- and 3-dimensional manifolds, and it lands in vector spaces. And so to a 2-dimensional thing, so to a surface, it assigns a vector space. And if I have a 3-manifold with boundaries given by a surface sigma and sigma prime, I get a linear map between the corresponding vector spaces. Right, so what that models is, you should think of this as sort of a finite version of a path integral. So this vector space you should think of as a space of states of the model on the surface sigma. It's like a Cauchy surface. But these vector space are always finite dimensional, right? So it's in that sense, it's sort of a finite model of a path integral. And the linear map you assign to a manifold, you should think of as evaluating the path integral on that manifold for a given in state, and then it produces some out state. That's what the linear map does. And again, if you see a topological field theory for the first time, it's quite fascinating that you can write these down explicitly. Right? So these maps that see of M, they see only the topology. So it's not a quantum field theory in that sense, doesn't depend on the metric, but they do see the topology and they are exactly compatible with composition. That's what's hidden in the word functor. And so you can write these down again exactly. So I want to do some examples. So I want to first look at a two-sphere with some marked points on them, and the marked points are labeled by representations, so by objects in my Ising category. And I'm saying that the vector space assigned to such a sphere, well, that's just the Hom space. How often can I fit the trivial representation into that tensor product? For example, if I have a sphere with two marked points and I label it with the representation sigma and sigma, then I get the Hom space of the unit into sigma tensor sigma, and that's 1 plus epsilon. So that space is one-dimensional, for example. Okay, for the two torus is three-dimensional. I'll not explain why that is. And I also want to compute some linear maps. So now you have to parse this picture here. So what I'm showing is a solid ball. Out of its middle, I've cut out a small 3-ball. So it's like a bombshell with the explosive material removed. And so it goes from the sphere with two marked points to the sphere with two marked points. And then inside the 3-manifold, I get these lines, these Wilson lines, which just stretch now vertically. And to this specific configuration, which is just a two-sphere with two marked points times an interval, my TFT assigns the identity map. Right? Again, it's not from a quantum field theory point of view, not too surprising, because it's a topological theory, so I can make the shell very thin, and the theory doesn't see how thin the shell is, so I'd expect this to be the identity. However, I can do now with my Wilson lines, I can do some complicated things. I can sort of exchange them and braid them past each other, and then you can again, the TFT computes for you an answer. For example, here you get some phase. And I'm not explaining you how you actually do these computations. I'm just saying you can. So this theory is well defined. One can read a big book, and then you can also do these computations at home if you want to. It's not difficult. It's just you have to remember some definitions. But you can also do more complicated things. You can say, rather than just having lines which connect the two boundaries, I could have some Wilson lines which just float inside my 3-manifold, like here. And if I label it by x can now be one of my objects, 1 sigma or epsilon, well, that will change what the answer is. And I'm saying that depending of if x is the identity, well, if x is the identity object, I get the identity. But if X is my other representation epsilon, it turns out I get minus the identity. And if I choose for X the third representation sigma, then this specific picture here gives 0. Right. And maybe do say one more thing. So I want to relate 2D 3FT and 2D CFT and 3D TFT. That I will need later briefly. It's saying that the basic idea is if you do conformal blocks on a surface sigma, then that's the vector space the TFT assigns to that surface. Then if you build a CFT correlator, it's built out of holomorphic and anti-holomorphic conformal blocks. For example, our 2-point function is the holomorphic component times an anti-holomorphic component, right? And that gives us modulus. And the way you model this with TFT is I'll just show the picture. For this 2-point function, you take your surface, you multiply the surface times an interval, and then you get a 3-manifold with 2 boundaries, sigma and minus sigma, orientation reversed. And then the marked points, which is where the field lives, you link them by the corresponding Wilson line. And now you have the freedom of drawing additional Wilson lines inside your 3-manifold, right? And these are now topological because we are talking about a topological field theory. And that's how in the TFT you model the conformal line defects of the 2-dimensional CFT. It's the Wilson lines which float inside the 3-manifold. And we understand now that because these are labeled again by my 3 representations, that these are precisely the 3 defects we saw in our lattice description. Right. And maybe on that note, I can just stop for the first part. Is that okay?
Yeah, it's okay. Let's reconvene in 10 minutes. So 3:20.
Okay. So that's some sort of coffee break at the moment, and I can also get a coffee.
Yeah, but not from us.
No, I want you to run here now.
Yeah, okay.
Give him coffee. We want him to be
Yes,
to be
give me
good for the
coffee.
next hour.
Oh,
Yes.
look there. Look, you have the proper coffee break. Look at that. Oh, no, you're taking it away. Unfair. Okay, I'll be back in a second.
Nie udało się udowodnić?
Szczerze powiedziawszy, też cały czas czekałem na definicję, bo mi brakowało definicji, bo ja nie robiłem notatek.
A którą? To ci od razu podam może. Jako definicja?
Znaczy,
Masz?
teraz nie pamiętam na
Co za definicja? Masz grupoid jego. Na przykład grupoid bar. Albo działania. Czyli to jest działanie rzut na drugą sprawę. Pytanie brzmiało tak. Patrzysz na centralizator w algebrze dyfeomorfizmów, w grupie dyfeomorfizmów G. Patrzysz na centralizator. Co ty miałeś? Mieliśmy ten homomorfizm grup z grupy bisekcji, dyfeomorfizmy G. To znaczy, że umiesz reprezentować bisekcję na strzałkach. W taki sposób, że bierzesz co to znaczy, bierzesz R beta na strzałce, zbierzesz strzałkę, tu jest jakieś takie strasznie szybkie wyrażenie, bierzesz beta, nastaje się S, G i tam -1, czy już teraz nie pamiętam, podawałem definicję.
Bo R i kolejne
No właśnie, no, drugie było proste, bo to było też L beta na G, to było beta na target G, kropka G. I składanie strzałek. I stwierdzenie brzmi tak, że centralizatorem obrazu grupy bisekcji względem R, right, jest L beta. Dlaczego to jest plausible? Jak popatrzysz sobie na centralizator w grupie dyfeomorfizmów, jak weźmiesz sobie, to na początku jest trywialnie, jak weźmiesz sobie grupoid nad singletonem, czyli grupę, no to zadajesz te pytania, co komputuje z prawymi wymnożeniami przez elementy grupy wśród dyfeomorfizmów grupy. No lewe wymnożenie. I to jest inspiracja. No i to wiemy dowodzić, prawda? No i twierdzę, że dla grupoidu działania to jest bardzo, bardzo podobnie z tego względu, że no ze względu na taką sfaktoryzowaną strukturę względem rozmaitości obiektowej, rozmaitości strzał. To bardzo, bardzo prosto rzecz wygląda. No poza tym ze względu na prosty charakter działania wyrażony w terminach samego działania lambda oraz operacji binarnej na grupie, charakter działania grupy bisekcji na G razy R. No więc stwierdzenie jest takie. Ja spróbuję w tym tygodniu dopisać te notatki, wkleić te notatki, ale tak dzisiaj to się pojawią notatki z tej. Tutaj to ostrożnie, bo to na pierwszy rzut oka to nie działa. To powinno być, to weźmy cudzysłów. Tu powinna być jakaś poprawka, bo popatrz, jak ja wezmę stors, nie, no to widać, że to z pierwszej, widzisz, tak, beta do -1 to strzałka do -1. To jest coś takiego. I wtedy beta do -1 to jest odwrotność beta złożone z T gwiazdka beta na argument. I teraz jak weźmiesz to masz beta złożone z T gwiazdka beta. I tu masz G razy beta od source of G. I teraz, jak policzysz target, przepraszam, jest -1. I teraz, jak policzysz target tego, to masz target beta złożony z target beta do -1, to się znosi i to się równa source of G, czyli to się składa. To jest to tak wygląda. Już bez. Przy czym, żeby musimy zaczynać. Żeby to pokazać dla ogólnego grupoidu, to musisz rzeczywiście wykorzystać to, że algebra Liego grupy bisekcji to jest algebra zwartonośnikowych. Musisz zawsze założyć, że M jest par. Zwartonośnikowych cięć algebrowych Liego, tego prawego algebra. Ale proponuję patrzeć na te dwa przypadki, bo nie wiem, czego takiego nie musisz zakładać. Znaczy nie musisz tego wiedzieć. Okay, I suppose we can restart. Please, Ingo. Go.
Okay, I just go on. Is that what I do?
Yes.
Okay.
Well, up to you, right?
No, now we celebrate. So very good. So that's the second part. So the second part is, as I say, a slide talk, and I will not focus on a specific model, but I'll try to make maybe more global statements. So I still, however, want to talk about line defects in two-dimensional quantum field theory, how they relate to certain categories and how they can tell you something about these quantum field theories. And I want to do something which I didn't discuss in the easing example, which is I want to say that you can gauge these. So if we understand them as these topological line defects or higher dimensional defects, if we are in a higher dimensional theory, if you understand them as symmetries, which may or may not be invertible, but still a symmetry, we can ask, can they be gauged? Can we go to some sort of invariant model under these symmetries? Okay. So that's the plan. Can you now see my little pointer? Does that work now?
Yes, we can see you.
Yes, okay, so that's at least the progress. Can I also change? Yes. So I explained an example of a topological defects in the Ising lattice model, but they also exist in quantum field theories. And so what you mean by a topological defect or a topological interface is in this my two-dimensional example here is that you have these two quantum field theories. They are related by this one-dimensional interface, and this interface is tensionless. You can locally deform it without modifying expectation values as long as you don't deform your interface across other insertion points of operators or fields. This, especially in higher dimensional field theory, has seen much recent activity in the context of topological phases of matter and symmetries of quantum field theories and so on. And so down here I've just listed recent reviews on this to indicate that many people are thinking about this, and really there are many, many, many papers in this direction. So it's a bit of a hot topic at the moment. The first point I want to make is that so as I said, this talk more algebra and little geometry. And the first point I want to make is therefore algebraic. So we've now got a structure in quantum field theory, which is these line defects. So what are they mathematically? And I'm saying that mathematically, always, they give you something called a bicategory. So it's sort of one level up from a category. So it's a two category, which may not necessarily be strict, with some additional structure, which I will not talk so much about, which are these adjoints. So what's a bicategory? And now it has objects, one morphisms, and two morphisms. So the objects are compared by one morphisms, and one morphisms are compared by two morphisms. But these, that's what it's called mathematically. But on the level of quantum field theory, they mean something very concrete. The objects are the different two-dimensional quantum field theories, which label the two-dimensional surface patches. The one morphisms are the topological interfaces, which can sit between one quantum field theory and the other. I mean, there may be none, but in the easing example, we have seen that these can be there. And then the two morphisms are topological point operators, which can connect two of these interfaces. right? And I am saying that whenever you've got the structure in the quantum field theory, you can use it to define or extract a certain mathematical object, which is this bicategory. And I will not, so I will occasionally mention these adjoints. They are related to the fact that we didn't see this in the easing example, but in general, my line defects come with an orientation, right? If you think of them as, for example, implementing a non-commutative group, well, then you need an orientation to see if you're acting with G or G inverse. And so then you can turn them around, and so this fact is encoded in the existence of adjoints. Right. So in particular, if I focus on the fact that the quantum field theory is the same on either side, then I'm looking at endomorphisms in this bicategory. So let me just call these topological endodefects, right? And now they form a pivotal because of these dualities, monoidal because there's a tensor product, and again, a category. So that's something we saw in the easing example. So then both of these sides would have been the easing model. And we had these three different types of topological line defects, and they came with a fusion operation, which would be this monoidal, which would be this tensor product. Okay. Now,
up to now, there has been no internalization or no extra structure on the space of defects. But if you think of them as generalizing group elements, then of course you could have continuous parameters. Are you going to talk about discrete defects only, or the problems with the continuous ones, or yeah?
I will only talk about discrete ones just in the next line. So at this point, indeed, I'd be allowed to have a continuous. So this could be labeled by just a Lie group, for example. Right? So then I still get a pivotal monoidal category because I'm not giving it much structure. It just says as a composition rule.
I have also a question. So you talked about fusion rules. This was like this D square is identity plus epsilon.
Yes. So
and
yeah.
And what is the plus in this case?
Right. So the plus I also didn't explain very much in the lattice model, right? So so the plus means if I hand you, maybe it's easier to so what does it mean to evaluate a correlator on one defect plus another defect? By this I mean you just take the sum of the correlators, right? So you just linearize. So it's like the correlator with the one defect plus the correlator with the other defect.
Yeah, but in the categorical sense, it's what is it?
And so in the categorical sense, it means that your category may have more structure, like in the what would come out of the easing example is that it's not just a category, but it's in fact comes with a direct sum relation. So it has.
I see. So monoidal is, you said, it's a tensor product, or
yes, monoidal is a tensor product.
So then in addition, some direct sum. And how is it called, such a category?
So well, let's see. So I would say that would be an additive category, because so what precise categorical structure you have depends on how complicated your theory is. I try to make a slightly different point in a moment. But if you have direct sums and additive form spaces, then it's something called an up category, and so if you have or an additive category.
Okay.
But really, at this point, I don't need the direct sum, right? I just need that if you take a product, if you take a fusion, then you've got another topological defect. It may or may not be that it can be decomposed into some way as a direct sum, but that sort of structure you discover afterwards. Anyway, so as Rafa said, I want to now not do the super general case, but I want to maybe generalize the finite group case. So like if you have a quantum field theory which has a group symmetry, that group could be a Lie group, for example, or some infinite dimensional group, like in gauge theories. But I want to look at the simplest case where I look at finite groups. But I don't want to look just at groups, but I want to include this non-invertible situation. And so the categorical thing which replaces a finite group is this gadget called a pivotal fusion category. So that's just words, but what that means is indeed that you have a direct sum operation, that your category is semi-simple, like representation theory of a finite group is semi-simple. And indeed, representation theory of a finite group is an example of such a category. Fusion means that it's does it have a tensor product, that it is semi-simple, and it only has finitely many irreducible representations, finitely many distinct ones. Right? So if you do a Lie group, it would not be a fusion category because you do have an infinite number of finite dimensional representations, but here infinitely many. Right? So that's in the sense in which it generalizes a finite group case. And so rather than trying to say, what's the entire symmetry of my quantum field theory, that may be hard to answer. I want to turn the question around slightly and ask, can I at least understand if my quantum field theory has a given symmetry F, which would be given by such a finite monoidal category, by such a fusion category. So I say that my quantum field theory has the symmetry F if there is a structure preserving functor from this category F to this monoidal category of endo defects. Right, so that's like having a group homomorphism from your finite group into the full symmetry group of your quantum field theory. Even if you don't know what the full symmetry group is, you can maybe still understand enough about it to be able to describe such a functor. Right, so and indeed, in conformal field theory, that's what happens. You typically have no idea what that entire category is. Like if you do WZW models, you have no control, but you can identify interesting fusion categories which can be embedded into the full symmetry. So that's something which does actually happen. Okay, so I say my quantum field theory has symmetry given by such a fusion category if I can realize the fusion category in terms of topological line defects. So the fusion of topological line defects corresponds then to the tensor product in here, and so on. Okay. So again, that's the data, fusion category. Pivotal was referring to the duals functor, which respects all the structure into my topological defects. Now, if you have done some category theory, then you will, when you studied functors, you will have met the words faithful and full of properties of a functor. Because a functor maps objects to objects and morphisms to morphisms. Now, on morphisms, so these are, in my examples, here will be vector spaces. It can be either injective or not. And if it's injective, it's called faithful. So no two morphisms can get mapped to the same morphism. And it may hit every morphism in the target or not. And so if it hits everything, it's called full. Right? So that statement translates into if I have this category, which I want to understand as my topological symmetry, which I'm implementing in the quantum field theory. If I take a morphism in here, so something in so that's the space of morphisms, I take one, then well, it gets mapped to a point defect between two topological lines, and the question is the space of all topological operators which can sit at that point, is this precisely given by the Somme space, or does it map into it, or do several maps here get mapped to the same thing here? And I'm saying if I'm in this case I'm in, where this is a fusion category, then faithfulness is guaranteed by just abstract nonsense. So it's always injective, but it may or may not hit everything here. Okay. So you can do this in 3D too. Then everything gets slightly more complicated. You get tri-categories, but at least it exists, right? As a mass framework. There's something called fusion 2 categories if you want to do 3D. If you want to do 4D, well, it's slightly more shaky. You have to define things recursively. So that's maybe more for the super experts. But at least in 3D, you can also do this if you want to. I'll say a little bit about 3D if there's time at the end. Okay, but I want to come back to 2D and I want to elaborate a little bit the point that a finite group symmetry gets generalized to this pivotal fusion category of topological defects. And I want to make the point that even if you apply the setting to just a group symmetry, it can tell you something new. So therefore, let G be a finite group. And now I have to take this finite group and I produce out of it one of my fusion categories. And the way I do this is I take finite dimensional complex vector spaces which are graded by this group. It's like a direct sum of finite dimensional vector spaces where each sum gets a grade some group element G of here. And the simple objects here are just one-dimensional vector spaces together with the information which grade they sit in, so which, and the grades, remember, are given by group elements. And the tensor product of these graded vector spaces, well, the grades multiply according to the product in the group. Right, so I've now produced, I've started to produce, giving an input of finite group, a fusion category. I've given this finitely semi-simple category with these simple objects, and I've described for you a tensor product. But there's more information there, which is something Rafa said in the very beginning, is that in a tensor category you also have an associator, which tells you how you reconnect. So if you think of these as line defects in the quantum field theory, you can try and change this configuration with 3 incoming lines and 1 outgoing line into that one. Right? And if you do that, it turns out you may encounter a phase. So they may not be exactly equal. And this phase, it turns out, defines a class in the third group cohomology of G with values in C star, invertible complex numbers. And indeed, this is something, that's my one connection with geometry. If you do these WZW models, then if you take a Lie group, then this G would be the center of the group, and this co-cycle you can compute gerbe theoretically from geometry. So you can get this from geometry, but I will think of this representation theoretically. So I will get these as algebraic data. Okay, so that's one information, but there's also another information, which is if you make a little loop of your defect and shrink it to a point, what number do you get? And that's called the dimensions, the quantum dimension of that object. So we have now, even in the group case, so let me go back one slide. So I fix a finite group, then I get all this data fixed for me. But now to understand how a finite group symmetry is realized in terms of defects, so to get this fusion category, I need to give extra information. And that extra information has 2 parts. It is this class in H3, and it is these numbers, the dimensions, the numbers assigned to these circles, so, which is a group homomorphism from G into C star. So what that means is that if you say my quantum field theory in 2 dimensions has a Z2 symmetry, well, there are actually 4 ways in which it can have a Z2 symmetry if you realize it in terms of line defects, because there are 2 choices for this class in H3, so that 2 inequivalent associators, but there are also 2 choices for this dimension factor. This gets a Z2. So there are 4 different ways in which a 2-dimensional theory can have a Z2 symmetry. And I've listed them here, and I want to talk a little bit about them. So one choice is this class in H3, that's my omega here. And on the non-trivial element, it can be either 1 or -1. And the other one is this dimension factors, and on the non-trivial element, it can be either 1 or -1. And the 4 fusion categories, the 4 pivotal fusion categories you get, the 2 graded vector spaces, a twisted version, twisted associator of that, or you get super vector spaces, that's the dimension -1, so that you get super dimensions, or a twisted version of super vector spaces.
What is the difference between Z2 graded vector space and super vector space?
Right. And it's in what I mean by the value, by this value on a circle here. So think of this, if this were a vector space, then the value on a circle would be the dimension of that vector space. Right. So in the Z2 case, even for the two-graded vector space, I just compute the total dimension. But in a super vector space, I have the difference, even dimension minus odd dimension.
Okay, understand.
And so these would be different physical situations because you could tell them apart. It's the value of this defect being a little circle which bounds a contractible disk. And so physically they also mean something slightly different. So we will get to this hopefully later, that if you have this class trivial, then the Z2 symmetry it describes can be gauged. If it's not trivial, then there's an obstruction to gauging, and you can't gauge that symmetry. You get a theory which is not well defined. Whereas this, whether you are in this and that situation, now again has some interesting geometry hiding behind it. If you start from a theory defined on oriented surfaces, and if you gauge this as Z2 symmetry described by vect Z2, by that pivotal fusion category, then the gauge theory is again defined on oriented surfaces. But if your pivotal fusion category is S-vect, well, then the gauge theory needs more information to be well defined. The gauge theory, you're gauging your Z2 symmetry, but in order for that to be well defined, you need a spin structure on your surface. So if you want
What
to
does
gauge
gauging a Z2 symmetry mean?
and right, I will get to that. Yeah. Can we maybe pause that question and I will describe that later, but I'm saying this here already, that there's gaugeable versus not gaugeable, and gives you oriented, gives you spin. So here I want to illustrate that these 4 different versions of Z2 actually do different things. And I'll say later what gauging is. Yeah, sorry. Are there other questions or comments? Good. So, so I want to do an example of a non-group case. So I've just explained in some detail the Z2 case. So we have 2 simple objects and they just fuse with Z2 rules. The simplest fusion category, which doesn't have group fusion rules, is called the Fibonacci category. It again has 2 simple objects, 1 and phi. And the tensor product of phi with itself is 1 plus phi. So that's no longer invertible, so that's not a group. And again, you can go and try and classify all theories with these fusion rules. You'll find there are 2 different associators, but there's only 1 pivotal structure now. So there are not 4 of these now, there are just 2 of these. Right, so this is an important mathematical question in a way. It's the analog of try to understand finite groups, try to classify finite groups. So that's difficult, but at least you can understand them sort of number by elements. And you can now ask the question, in 2025, up to how many simple objects do we know all pivotal fusion categories? And the answer is 3. So that question is actually quite hard. And it's not known what are all pivotal fusion categories of which have 4 simples. So even then we don't know what are all possible symmetries of a 2-dimensional quantum field theory. Okay, that's just as an aside. Okay, back to my setup. So I now want to discuss, so what good does it do you if you know that your theory has a given symmetry? So if it has a given, say, pivotal fusion category as symmetry in that setup I described. And I want to go through some examples. One example is if my quantum field theory is itself topological. So I've got a 2-dimensional topological field theory. Then that's mathematically, it's one of these symmetric monoidal functors, but now one-dimensional manifolds and 2-dimensional manifolds. And so my quantum field theory, I suppose it is topological, and it has a unique vacuum. So the state space assigned to an S1 is 1-dimensional. So that means a very, very simple theory. So it's one state, and so for each surface you just get some number. Then you can ask such a theory, what kind of topological symmetries can it have, such a simple theory? And it turns out that the only pivotal fusion categories you can realize by a two-dimensional topological field theory with unique vacuum are ones which mathematically have a property which is called that they admit a fiber functor. Explicitly, it means that they're given by representation of some Hopf algebra. For example, they could be given by representations of a finite group. But the category we saw in the Ising model does not admit a fiber functor. So this category with 1 s and d squared is 1 plus s cannot be the symmetry of a 2D TFT with a unique vacuum. So conversely, if you know at least one thing about your quantum field theory, or two things, which is one, it has unique vacuum, and two, it realizes this Ising topological symmetry. You know it's not topological because you can't realize that symmetry in a TFT. So that sort of reasoning can teach you things about quantum field theory. Let me make a related point in conformal field theory. You can ask the following question. So what is the unitary conformal field theory, again with unique vacuum, of the smallest central charge such that you can fully faithfully realize one of your topological symmetries? So let's look at the Z2 symmetry we had. So I said there are 4 versions of this Z2 symmetry. So let's look at 2 of them, vect Z2 and the twisted vect Z2. And it turns out the smallest theory which has vect Z2, well, that's the Ising CFT. That's the one in S which we met. But if you have the twisted version, then you can't realize it below central charge 1. Then you need at least central charge 1, it turns out, just by inspection. Right? I don't have a good abstract argument. But this sort of slightly hidden datum of the symmetry, which is how do you have to reconnect defect lines? Well, if you know that it's this twisted version of the Z2 and it's realized in your CFT, you know it has at least central charge 1 if it's unitary. Right? So these symmetries, by taking into account the fact that they have more information than that just a group, can tell you also more things. Good. Now I want to go to these. Sorry, let me go back a slide. So that's what I wanted to say about the setup of topological symmetries, which may be not invertible and are realized by topological defects. And now I want to come to the part which hopefully answers an earlier question, which is how can you gauge such topological symmetries? And so this goes by 3 different names. One is generalized orbifolds because it generalized orbifolding by a group symmetry. Closely related is gauging because orbifolding is a version of gauging a discrete symmetry. And if you come from a TFT background, there's a third name, which is an internal state sum model, which is also very natural. So what's the idea? We take a quantum field theory. It now has maybe not just dimension 2, but dimension 3, 4, 5, whatever, and we fill it with a foam of defects of all dimensions. So like in my 3 dimensions, I have here an actual foam. And I want to choose the conditions of these defects, surfaces, lines, and points in such a way that changing this foam doesn't change the value of correlators. And then I have the prescription that I get my generalized orbifold by taking my original quantum field theory, putting such a foam of defects and evaluating. And then that's the orbifolded theory or the gauged theory. Okay. I'll go through this dimension by dimension in some examples. But let me first again collect the data I need in general. So it comes in different flavors. Let me not go into this. But if I want to do this procedure of gauging a topological symmetry for a d-dimensional quantum field theory, then the data I have to collect is 1 defect of dimension d-1, 1 defect of dimension d-2, and it turns out 2 of dimension 0, but again, that's a technical detail. And the conditions are that the configurations have to be invariant under Pachner moves, or because I work with something dual to triangulations, dual Pachner moves. and because all my defects will be oriented, these partner moves are also oriented. Again, technical detail. Okay, let's go dimension by dimension. One dimension. So I've got a one-dimensional quantum field theory, that's also known as quantum mechanics. So my space, I'll only work Euclidean, so I've got a one-dimensional space. Then my defects are zero-dimensional, and then it stops. And I want to say I make a foam of one-dimensional defects. Well, that just means marking some points. But I want the expectation value of such a configuration to be independent, firstly, of where I put these points, whether they are topological, but also of how many points I've actually put. And so I must be able to combine 2 points together to just give me one new point. And so I need an identity like this. A squared has to be A. So in one dimension, my condition on my defect is that the corresponding operator is an idempotent. And then so what the gauging does, it just projects to the image of that idempotent. Okay, 2 dimensions more interesting. So there my foam now consists of lines which are connected by in my convention 3 valent junctions. And I have to be able to change one such foam into any other foam, and it turns out I can do this by 2 local moves. Well, actually many local moves because they have to work for all orientations, but so of 2 types. One is this fusion move, which reconnects a lattice, or which reconnects my graph here locally in this fashion. And the other is the bubble move, which allows me to emit such a defect bubble. And so categorically, remember that I've got this monoidal category, which describes these line defects. That means inside this category, I'm pointing at something called asymmetric delta separable Frobenius algebra. And algebra is because that's a little bit like an associativity condition. And if you translate it back to the categorical side, it's exactly an associativity condition. Then these vertices can give you a product and a co-product, and delta separability will be this identity here. So that's in 2 dimensions, and in 3 dimensions, well, it just looks more complicated. So I've got some 3-dimensional foam here, and again, there are local moves, which if your correlators are invariant under these local moves, then the precise shape of the foam does not matter, because you can transform any one such foam configuration into any other by using such moves. Okay. So what can you now prove? So if you do this procedure of gauging a d-dimensional topological field theory, so let me go back 1 slide. Suppose I've got a topological field theory with these surface, line, and point defects. Then, as I said, what gauging means is I get a new theory by taking my old theory and inserting such a foam. Then, because my conditions ensure that the precise choice of foam doesn't matter, well, then that's the same as evaluating my new theory on the given manifold. Right? And that theory I call the gauged theory. And if you were to do this in the finite group example, it's indeed gauging a finite group symmetry. So if you do this in a d-dimensional TFT, then the output is again a d-dimensional TFT. So that I'm allowed to call this a theorem because I have a mathematical description of d-dimensional TFTs. But the same will work and is used also for d-dimensional quantum field theories, but I can't make it into a theorem because I don't have a mathematical functorial description of d-dimensional QFTs to which I could apply this. But intuitively, it's the same procedure. Take your quantum field theory in d-dimension, put a foam, evaluate. Okay, so that is what gauging means. That's what so if you gauge one of these topological Z2 symmetries, for example, then if I go back, then this purple line would be the sum of the simple object 0 and the simple object 1 in my category of what's the Z2 symmetry. and then one can compute what these vertices are. And you would find that if you try to do this in vect Z2, you find the solution for these conditions. And if you do this in vect Z2 omega, then you do not find a solution for that condition. And so you
Ingo,
can't, yeah.
sorry for interrupting. What is the precise mathematical definition of a foam in this work?
Yeah. So I'm using foam to not say dual, to a triangulation.
Okay.
You can, so that's sort of the shortest way of saying it, but really you need a cell complex where all cells are contractible.
Ingo, I think if I may just make one comment.
Yes.
Because this whole idea of a foam, and I think it is enlightening to mention it, goes back to the 1950s. It actually goes back to a construction by Cartan, which was later propagated by Borel. I mean, if you think of the standard gauging procedure as replacing, as a model for the orbis, or the field theory on the orbis space of the action of a group, which goes via the associated bundle construction. If you now think of sections, global sections of the associated bundle, you can think of them as locally given by smooth profiles in the original manifold before the gauging, but they are now linked by defects at which the discontinuity appears, and then the jump is measured by the action of the group. And then in order to gauge a theory, you have to allow for any principal bundle as the point of departure of this mixing construction due to Cartan. And this decomposition into cell is none other than a decomposition into opens over which the principal bundle trivializes. So I'm not saying anything new, but I think it's very enlightening to have this old picture of the gauging in mind, where you just take, roughly speaking, a sum over all isoclasses of principal bundles, of which then you can think of probing sigma points, where sigma is your spacetime, in the Ionian sense, sigma points in the universal mixing construction, right? In other words, in the classifying space of the group, of which the universal principal bundle sits. So I think it's actually quite. It warms one up to this foam idea.
Okay, so then you would say here we have a smooth configuration, and across this line it jumps, right?
Yeah. It jumps in a way controlled by your symmetry models. So a group maybe, or what not.
And so there's one thing one has to do, is that for me these lines are already like a sum of group elements, right? So you would you would expand out that sum, so you get a big sum where these lines
over the
in each term, then
bundles, basically. Yeah.
That would implement the sum
and
of a principal.
And if you don't do that, as Hori once computed in his path integral approach, if you don't do this sum over the isoclasses of principal bundles, then you have anomalies in the quantum theory, like fractional dimensions of the vacuum, or no vacuum at all kinds of pathologies. So you really have to sum over all contributions from all isoclasses. Yeah.
And so then sort of the new maybe the new point of view, by thinking about from this defect point of view, is that these may now also have summands which are not invertible, which is something I don't have a geometric interpretation for anymore, because then I lose this bundle interpretation.
Ingo, if I can just continue, I mean, why I am asking this, because if you work by topological notions, right, you can have a simplicial decompositions, for example, in the PL category, or cell decompositions, but in higher dimensions, that's not equivalent to the smooth category, right?
Right.
Well, I'm asking whether this decomposition, this notion of foam, you are imposing some kind of piecewise smoothness condition for the decomposition.
And
will this construction, for example, in 4 dimensions, be sensitive to the differentiable structure? That's what I'm asking.
So,
don't answer. Will it steal the differentiable structure?
I would say, so what's happening is slightly different. So the overall manifold with its smooth structure is given, right? And I am embedding the foam.
and you are embedding it in some kind of piecewise smooth way, so a way that depends on the choice of differential structure on your manifold.
But the differential structure, so that's part of the data, the overall differential structure on my full four manifold. I'm not trying to fix it separately here and asking how to connect it.
Okay,
on the whole orange patch, I've already got my smooth structure.
Okay, so you are sensitive to differential structuring for this.
Well, in principle, of course, for the TFT, I've got 0 examples, right? But I mean, if you have an example of a TFT which is sensitive to the smooth structure, and you do have some defects in it, you could produce other examples which are sensitive to the smooth structure. That's maybe a way of saying.
Witten, for example, yeah.
Okay. So you could have Rosansky-Witten, and maybe you can have gauged versions of Rosansky-Witten by doing this construction. But I have, again, no examples. So we did this, and I'm kind of running out of time. So maybe I do this one thing and then I stop. So I want to say that being related by gauging defines an equivalence relation on quantum field theories. You can ask, can I obtain one quantum field theory by gauging a topological symmetry of another? And there's a simple criterion. What's one of these finite symmetries, right? So there's a simple criterion for when this works. And that is if firstly, you have to find a topological interface between your two quantum field theories. And that has to have the property that its bubble, the value on a small bubble of that interface is invertible. And if that's the case, then you can obtain one theory from the other by gauging. And the way this works is very similar to this Ising model computation on the torus we did. You start with one theory, you insert lots of little bubbles of the other theory, then you expand the bubbles, and now this starts to look like these walls. If you fuse these together, they become surface and line defects, which give the data the defect data by which you can gauge. So QFT1 has become a gauging, is obtained by gauging from QFT2. Maybe I skip this. So I want to say that procedure is actually quite powerful in conformal field theory. So in rational conformal field theory, any two rational conformal field theories with a given fixed rational symmetry are related to each other by this gauging. So if you do SU2 Wess-Zumino-Witten models, then you may know that they are sometimes that they're sort of classified by an ADE classification, and at a fixed level, all these Wess-Zumino models you can construct of type AD or E, they are connected to each other by this gauging procedure. That would not be true if you were just allowed to do group orbifolds. So if you do this, if you wouldn't include non-invertible defects, that statement would not hold. But if you include them, then indeed all of them are connected by this procedure. Okay, maybe the 3D I skip a little bit. Skip, and I just summarize. So we learned in part 1 that we can, even in the very simplest lattice model, you can construct interesting topological defects and reason about them, even though mathematically we're just talking about finite sums. Then we said these defects generalize the notion of symmetry by replacing what was a group by these monoidal categories, and finite groups by these pivotal fusion categories. And we had some examples that knowing that a given fusion category is realized by topological defects can teach you information about the quantum field theory. But you can also use these topological defects to turn old theories into new ones by this gauging procedure, and it sort of stratifies your space of quantum field theories into equivalence classes of theories related by this gauging. And yeah, maybe with that, I stop and thank you for your attention.
Okay, so there have been many questions along the way, but are there any questions now or comments?
I'd like to ask a sort of very general question. So Is it understood how this might relate to non-commutative geometry? So if you think of defects, so if I want to drop this piecewise differentiability condition, right, which I just mentioned, I could try to somehow consider the category of laminated metric spaces, for example, which has a connection to T-star algebras, non-commutative geometry, and so on. Has anybody tried to generalize the notion of defect, topological defects to that situation? Then starting from zero, from the category of borders with topological defects, but consider a notion of topological defects which is based on laminations rather than to somehow.
So I want to say no, but I also don't understand the question well enough. So rather than just marking a line, you want to have like a lamination of your surface?
Yes.
And why do you say non-commutative geometry?
Well, I mean, there's a connection between laminated metric spaces and metric spaces in the sense of spaces with distance.
Okay.
Topology comes from a distance.
So
C-star algebras, non-commutative geometry, and so on. So it would be somehow an interesting connection between fields if it can be made, because somehow in higher dimensions, this is in some sense you have a choice of whether you want to be sensitive to the differentiable structure and you want to go further into metric spaces, non-commutative topology in the sense of Kohn and that sort of stuff. So it's a natural idea to pursue.
So I don't know the answer to that question, but I want to maybe say one thing where one might want to look. So suppose we are not in this. Suppose we would have a Lie group as a symmetry, right, rather than a discrete group. Then if you label a line by a given group element, well, it should also be possible to just smear this out into a sort of bump function, right? And then it's less clear what you mean by a vertex of such. So if you take your defect line, you smear it out a little bit, you should still be able to talk about vertices in some way. And that sounds a little bit like what you want to do with your laminations. But I'm not aware of anybody having actually worked that out. In particular, what would that mean if you have a continuum but of non-invertible objects? So if you have more complicated tensor product rules. So I agree. So that's an interesting question, and I'm not aware of it being worked out.
Okay.
But people in this topological symmetry field, people are thinking about what does it mean to gauge a continuous symmetry from this point of view of topological defects. So there are papers.
So if I may ask another question, much smaller. So what if you look at the category of representations of a discrete but not finite group? So in that case, it's not necessarily reductive, but you still have some reasonably good properties, I think Noetherianness and so on, which are almost, I mean, rather close to reductiveness.
Right.
Has this been considered as a model of symmetries?
Yeah, certainly. So certainly, people are so yes, not maybe so much as a piece of math, but in examples in quantum field theory, people are looking at symmetries where the underlying category isn't finitely semi-simple. Right, so that goes in several ways. You can have an infinite number of simple objects. So there's an infinite number of different defects if you want. People are that has been looked at in examples. You could have maybe non-semi-simple non-semi-simple situations. That's been looked at in the context of TFT. You could have continuous groups, but I'm saying sort of that's a study on the level of look in my quantum field theory this happens, not like a mathematical theory.
But that's somehow very natural if you think of arithmetic groups, right? For example, the modular group. If you would like to somehow extend this theory so you can make nice constructions with uniformization and things like that, this would be rather natural direction as well.
Okay. Yeah.
Okay. Thank you.
Thank you.
I'm afraid I have to break the atmosphere. Put it down on me because we have people breathing down our neck. And we don't like that. So, Ingo, thank you very much. It was very nice to see you, even from that distance. And thanks for a nice talk. And I hope we can see you again before long. So, thanks a lot.
Thank you for the invitation. Good to see you. Goodbye.
Ciao, ciao.
Thank you, Ingo.
Bye-bye.
Bye-bye.
Bye, Kalin.